Welcome, and thanks for joining this introduction to Infocomm engineering. In this presentation, we'll walk through the fundamentals, key technologies, and practical applications that drive modern information and communication systems. I'll highlight concepts like networking, signal processing, wireless systems, security, and emerging trends to give you a clear roadmap of this field. This contents page outlines the journey ahead, covering an overview, communication fundamentals, networking basics, signal processing, wireless systems, protocols, system design, security, future trends, and a final summary. Think of this as our roadmap, and I'll connect each part so you can see how the pieces fit together in real-world Infocomm engineering. Let's begin with a high-level overview of Infocomm engineering so you can see the big picture. This section explains how information technology and communication systems merge to enable data exchange, networking, and digital services, and why that integration matters for industries, cities, and everyday applications that rely on seamless connectivity. When we define scope, Infocomm engineering blends hardware, software, and networks to move and process information efficiently. Historically, it evolved from telephony and computing into modern digital networks, and today, it powers applications like smart cities, IoT, and multimedia services that shape business and daily life across sectors. Here are the core technologies that make Infocomm work: communication systems for carrying data, information processing for transforming and managing that data, and networking technologies for connecting devices and routing traffic. Together, these areas enable reliable transmission, efficient decision-making, and the infrastructure needed for modern digital services and applications. Infocomm opens many career paths across telecom, IT services, cybersecurity, software development, and network infrastructure. Roles range from network engineers and system analysts to security specialists, and the field keeps evolving with AI, 5G, and IoT, offering growth opportunities for people who combine technical skills with problem-solving and communication. Now we move into communication systems fundamentals, which form the backbone of how information is transmitted. This section focuses on signals and systems, the difference between analog and digital approaches, and core modulation techniques that let engineers send data reliably over various channels under real-world constraints. At the heart of communication systems are signals and the systems that process them. Signals represent information over time or space, while systems analyze, filter, and modify those signals. Understanding this relationship helps you see how data is shaped, transmitted, and recovered, which is essential before diving into modulation or coding methods. Transmission media decide how signals travel, whether along cables or through the air. Wired options like twisted pair, coax, and fiber provide reliability and security, while wireless media add mobility and coverage, but face interference and security challenges. Optical fiber stands out for long-distance, high-bandwidth links used in backbone networks. Data encoding and decoding let us compress, protect, and recover information during transmission. Source coding reduces redundancy for efficiency, channel coding adds controlled redundancy for error detection and correction, and error handling techniques like parity checks and Hamming codes help ensure integrity across noisy channels. Now we'll switch to networking fundamentals, so you can understand how devices interconnect and exchange data. This section covers network types, topologies, protocol models like OSI and TCP/IP, and the main devices, routers, switches, hubs, and gateways, that make packet delivery and internet working possible in modern systems. Networks vary by scale and topology, from LANs for a small area to WANs connecting broad regions, and topologies like bus, star, and mesh influence performance and fault tolerance. Protocols define rules for communication, with standards like TCP/IP and HTTP enabling interoperable data exchange and efficient routing across networks. The OSI and TCP/IP models break complex networking functions into layers, so each layer can handle specific tasks. Layered architectures simplify design and troubleshooting as the physical, data link, network, transport, session, presentation, and application layers each contribute to successful end-to-end communication between systems. Network devices perform distinct roles. Routers forward packets between networks using IP addresses, switches manage data flow within a LAN using MAC addresses, Hubs broadcast to all ports, bridges filter traffic to reduce collisions, and modems or gateways translate and connect different network types for wider interoperability. Next up is signal processing basics, which explain how raw signals are shaped and analyzed for clear communication. We'll look at analog and digital techniques, filters, Fourier analysis, and how image and audio processing fit into communication systems to improve quality, reduce noise, and enable multimedia services. Analog signal processing uses filters and amplifiers to refine continuous signals, removing unwanted components and boosting desired frequencies. The Fourier transform helps decompose signals into frequency components for analysis and filtering, while noise reduction techniques improve clarity without distorting the original information significantly. Digital signal processing converts continuous signals into discrete data through sampling and quantization and then analyzes them using techniques like the discrete Fourier transform. DSP enables compression, robust error handling, modulation, and many practical communication tasks that ensure reliable, high-quality transmission across platforms. Image and audio processing add another layer to signal work, focusing on visual and sound data. Image techniques include filtering, edge detection, and segmentation to extract meaning, while audio processing handles noise reduction and speech recognition, both critical for multimedia communication and synchronized delivery over networks. Shifting to wireless communications, this section explains systems that send information through radio waves and the architectures that support them. We'll cover technology evolution, cellular concepts, Wi-Fi and Bluetooth, network components, spectrum usage, and the challenges in ensuring coverage, capacity, and security for mobile connections. Wireless systems have evolved from simple analog links to sophisticated digital networks capable of high data rates and low latency. Cellular networks divide coverage into cells to reuse frequencies and improve capacity, while Wi-Fi and Bluetooth provide local connectivity for a wide range of devices and personal area networks. A wireless network's architecture includes mobile devices, base stations, access points, routers, and core networks that coordinate coverage and data flow. Efficient frequency spectrum use, interference management, and mobility support are essential, and engineers must also address challenges like attenuation, security vulnerabilities, and limited bandwidth. Emerging wireless technologies are transforming connectivity. 5th-generation networks deliver ultra-fast speeds and low latency. IoT extends networks to billions of devices for automation, and satellite communications provide global coverage for remote areas, all of which drive new applications and system design considerations in Infocomm engineering. Now let's focus on data communication techniques and networking protocols, the rules and methods that make data transfer efficient and reliable. We'll explore serial and parallel transmission, synchronization methods, multiplexing, common protocols like HTTP and TCP/IP, addressing and subnetting, and network security practices for real deployments. Data transmission comes in serial and parallel forms, with serial sending bits sequentially over a single channel and parallel sending multiple bits simultaneously on separate lines. Synchronous transmission aligns data with a clock for continuous streams, while asynchronous sends individual bytes with start and stop bits for timing. Multiplexing techniques let multiple signals share a single channel, improving bandwidth efficiency. Time division multiplexing interleaves time slots, while frequency division multiplexing allocates different frequency bands. These methods are fundamental for carrying numerous conversations or data streams over limited physical media effectively. Protocols like HTTP, FTP, and SMTP define how applications exchange data, while IP addressing and subnetting identify devices and partition networks for efficient routing. Network security protocols such as SSL/TLS ensure confidentiality and integrity, protecting data in motion through encryption and authentication mechanisms. Effective network management keeps systems reliable and performant by monitoring traffic, detecting faults, and configuring devices. Performance analysis helps optimize resources. Fault management isolates and resolves issues, and proper configuration practices maintain security and ease of maintenance for stable data communication environments. Moving into Infocomm systems design, we'll look at how requirements are gathered, architectures laid out, and systems tested and maintained. This section bridges theory and practice by showing how to define objectives, balance user needs and constraints, choose hardware and software components, and plan for integration and upgrades. System requirements analysis begins by defining clear objectives and user needs, then documenting constraints like budget, regulatory limits, and environmental factors. Functional specifications describe expected behavior and interfaces, which guide design decisions and ensure the final system meets stakeholder expectations and performance targets. System architecture combines hardware elements such as processors and networking equipment with modular software components and integration strategies. Good architecture emphasizes scalability, maintainability, and clear interfaces that enable middleware or APIs for flexible deployment and efficient system evolution over time. Testing and implementation are where designs become reality, using unit, integration, system, and acceptance tests to verify functionality and performance. Deployment approaches can be phased or pilot-based to reduce risk, and ongoing maintenance and upgrades are required to keep Infocomm systems secure, reliable, and aligned with new requirements. Security is central to Infocomm engineering, so this section reviews threats, cryptography basics, and practical measures to protect systems. We discuss common vulnerabilities, why security matters for data integrity and privacy, encryption approaches, certificates, and network defenses like firewalls and secure protocols to mitigate cyber risks. Security challenges take many forms, from malware and phishing to insider threats and denial of service attacks. Systems often suffer weaknesses like poor authentication or outdated protocols, so prioritizing security helps protect data integrity, preserve privacy, and maintain trust in communication systems amid evolving threats. Cryptography underpins secure communication by converting readable data into coded form to prevent unauthorized access and by using digital signatures and certificates to ensure authenticity. Symmetric cryptography is fast, but requires shared keys, while asymmetric methods ease key distribution at the cost of higher computational load. Network security measures include monitoring and access control to block unauthorized traffic, intrusion detection systems that flag suspicious activity, and secure protocols like SSL/TLS to encrypt data in transit. Best practices such as strong password policies, multi-factor authentication, and regular patching help reduce the attack surface. Looking ahead, emerging trends and future directions show how Infocomm engineering will change with AI, cloud, virtualization, quantum communication, and sustainable technology. This section highlights how these advances enable smarter networks, new services, and the need to rethink architecture, security, and management for next-generation systems. Artificial intelligence is increasingly integrated into network management, predictive maintenance, and security, while machine learning improves routing, traffic prediction, and anomaly detection. Smart systems combine AI with communications to enable real-time decision-making, adaptive responses, and improved user experiences across Infocomm applications. Cloud computing and virtualization reshape infrastructure by enabling scalable, flexible resources and virtual network functions that reduce hardware dependency. The cloud offers cost efficiency and easier deployment, but it also brings challenges around latency, security, and integration that engineers must address in system design. Future technologies point toward quantum communication for ultra-secure links, next-generation networks leveraging AI and edge computing for ultra-fast and reliable services, and green technologies that prioritize energy efficiency and sustainability in network design to reduce environmental impact while driving innovation. As we wrap up, this summary and review will pull together the key concepts from the course. We'll recap core principles of Infocomm engineering, the major technologies covered such as networking, signal processing, wireless systems, and security, and highlight practical takeaways to apply in projects or further study. Core principles of Infocomm engineering center on integrating information technology with communication systems to enable efficient data transmission, smart network architecture, and signal optimization. Keeping these foundations in mind helps you design systems that balance performance, reliability, and scalability across diverse applications. The major technologies we covered include communication systems, networking protocols, signal processing methods, wireless architectures, security mechanisms, and emerging trends like IoT, 5G, and AI. Understanding how these technologies interact gives you a practical framework for solving real engineering problems in connected systems. Practical applications range from smart cities and healthcare monitoring to industrial automation and network security solutions. Real-world case studies show how Infocomm engineering improves connectivity, data management, and decision-making, driving efficiencies across sectors like manufacturing, telecommunications, and public services.